Hi everyone, welcome to this session on Object Tracking in Python. I'm Stephen Cross, I'm from the Wolfson Bioimaging facility at the University of Bristol. This session is part of a larger course that we ran in December 2019 at the University of Cambridge and is focused on bioimage analysis in Python. If you've just stumbled across this video, it's definitely worth checking out the rest of the material. There's a link to our GitHub in the description below. At this point, it's also worth going to that GitHub either way, just so that you can download the Jupyter Notebook and this PowerPoint so you can go along at your own pace. In this session, we're going to assume that we're already able to detect objects and extract their centroid coordinates. The aim here is simply to take these pre-detected coordinates and track them through multiple frames. The data we're going to use today comes from the Cell Tracking Challenge. On the screen at the moment, you'll see the original source for this data. What we get from the Cell Tracking Challenge is a sequence of images showing a series of cells dividing, and we also get some text coordinates for each of those cells over time, and that's what we've plotted here with the red dots. So what we get is it's just x, y, and t coordinates, and what we want to do today is to be able to take these separate x, y, t coordinates and link them through time. One of the provided functions I've given in the repository will allow us to plot each cell's track with a unique color. So that's what we're seeing here. Let's just play that again. So you can see each of the cells moving along and its track being displayed by a color trail. Okay, so I'm just going to summarize the steps that we're going to be using today. This is simply an overview, and I'm going to be describing each of these in much more detail as and when we get to them. It's also worth noting that there are many ways to approach any analysis problem, and it could well be that the way we're going to work through this today isn't what you would have intuitively done yourself. This is fine, and once we've finished today, you can obviously go back and work through this, reconfigure the workflow in a way that makes more sense to you, and then compare the results, see whether you get the same kind of results using your own technique. So to start, what we're going to do is we're going to import the coordinates that we received from the Cell Tracking Challenge. On the left-hand side, you can see a cropped-down version of the file that we get from the Cell Tracking Challenge. The first column, the one that hasn't got a label, is simply the row number. Then the next one along, the ID number, is a unique ID number specific to each time point instance of a cell. So these ID numbers don't infer any sort of tracking knowledge. Your next two columns, X and Y, are simply the centroid coordinates of each cell, and then the frame column is the frame in which that cell instance appeared. Note that the numbering here starts from 0, as is common in a lot of programming languages. We also have a column which indicates what the area, the measured area, was for each cell, and this is something we can use to enhance our tracking, i.e. trying to choose cells for linking which have similar area measurements. And then the final column here is just blank at the moment, so this is where our track IDs will go. So this is where the same cell in different time points will be given the same track ID. And you've already seen this video, but this is just the centroid coordinates that we've received from the Cell Tracking Challenge plotted on top of a small section of the video that we've received. The next thing we're going to do is going to initialize the tracks. So for the first frame, we don't have any tracks that we're going to be linking back to. So we can assume each of these cell instances is the first time point of that track. So to start with, they're 0, and then we just give them unique numbers, in this case from 1 to 23. So at this point, we enter a loop. This loop will continue until we've finished analyzing every single frame. So for the next section, what we want to do is to identify which tracks have previously been identified that we can link back to from our current frame. Now obviously we've just looked at frame 0, or the first frame, and we'd be linking anything to the second frame. However, for the purpose of demonstration here, I've actually skipped forward a bit in time, and now we're currently trying to link things to frame 50. So if you see at the bottom of this table, frame 50 have no track IDs, they're all still set to 0. So what we do is we say, right, we're going to find the most recent time point instance of every track and extract out the row coordinates for that. So we can see here that in frame 49, we've got IDs for 3, 9, 4, and 8. In frame 48, we've got available IDs 5 and 6. And in frame 47, we've got ID 2. So these are the most recent frames in which all of those unique track IDs were detected. We also need to identify the rows which correspond to the current points. So this is just anything in the current frame which is set to 0. So at this point we've got the row indices in the table for the most recent instance of each of the tracks, and also the row indices for all of the current points, i.e. those in the current frame. What we want to do now is determine what the optimal assignment is, i.e. which of the current points links up best with the previous track instances, simply based on, at this point, their spatial separation. Now we can use other metrics in this later on, but for now we're just doing it based on distance. So for this we're going to use the Kuhn-Munkres algorithm, also known as the Hungarian algorithm. As I mentioned previously, not going to go through this in any detail at the moment because we will be looking at it in greater depth when we get to it. Suffice to say for now, all we do is we take all the previous tracks and the current points and calculate all the combinations of linking distances, and then take the combination which has the shortest sum distance. The current points then inherit the track ID of the track instance that they were linked to, and we just repeat this until we have no more frames to process. At that point, we then have the option to output in any format that we want. So we have our table, which is same as the input, but now with that additional column of track ID, or we can output a video. So in the repository, there is a function which allows us to plot the video with the centroids as red spots, and also color-coded lines for each of the tracks. This session is broken down into 10 exercises. Each of these exercises is going to introduce a new concept which together will form a single functional tracking workflow. If you haven't already done so, now is definitely the time to go to that GitHub link in the description below and download a copy of the repository. For the tracking element of that repository, you'll find 2 Jupyter notebooks. One, the general exercise sheet that you'll be working from. This one's labelled student version. You'll also see an instructor version, which is basically the same thing, but with some model solutions included. So if you do get completely stuck, you can always go back to that and see if you can get some hints as to where you might be going wrong. You don't need to use Anaconda for this. However, if you do, in the GitHub repository, you'll also find an environment.yaml file, which will allow you to set up an environment in Anaconda, which has all the correct dependencies. So it just makes getting started that little bit easier. There's instructions on how to use that YAML file also in the description for the GitHub repository. In terms of what the Jupyter notebooks look like, there's the series of exercises broken down like this, and the first couple are slightly different, so I'm just going to skip to the exercise listed number 2. So you've got a brief description of what you'll be doing in that exercise, a bullet point set of of aims, and then you've got notes which might give you some additional hints on how to proceed. Typically, each of the exercises involves you taking a predefined method format and then inserting code. So here we're taking coordinates and a frame number, and we're trying to extract out the row indices from that coordinates table corresponding to all coordinates in this current frame. And then the reason for using this format, this sort of prescribed format, means that you can then go into this test space where hopefully you shouldn't need to edit any code. You can simply run this, and assuming that your code in the method is correct, this should output a description or show you that what you've done is correct. Okay, so let's get cracking with the first exercise. I say first exercise, but this is actually just listed exercise 0 because it's simply just making sure that our Jupyter environment is working correctly. So in this, aims are to import any functions we're going to be using later on, to set numpy and pandas to display numbers to 2 decimal places, just to try and keep the output section of the notebook tidy, and to also create an infinity variable, which we'll be using later on during tracking. I put infinity in inverted commas because it isn't actually a representation of infinity. It's not a special value. It's simply just a very large number, much larger than anything else that we will be finding in this notebook. So right now, if you want to go over to the student copy of the Jupyter notebook and have a go at doing exercise 0, then we'll restart and I will talk through what needed to be done. Right, so let's take a look at what we needed to do for exercise 0. So if we go to this, this was simply just a case of running the different cells. So the first one here is importing the libraries that we're going to use. The next one is setting the number of decimal places for display for pandas and NumPy. And then the third one here is for creating that infinity value. The last one here will download the image data from the Cell Tracking Challenge website. You can see the URL here. And if you want to know more about the Cell Tracking Challenge, the description at the top of the file has a link there. First time we run this, it's actually going to have to download all the information. So you can see this progress bar here. I'm just going to quickly skip this on because we've got quite slow internet. And we're done. So you can see here it says unzipping complete. So all is good to progress on to exercise 1. As with exercise 0, exercise 1 doesn't require us to write any new code. All we're doing here is loading in the coordinates and the videos that we've downloaded from the Cell Tracking Challenge and then displaying them as red dots over the original videos, much as we saw earlier on in this presentation. When we run this code, what you should see is something like this on the right hand side. So this is an inline matplotlib plot within the Jupyter Notebook, and we get a little scroll bar here which allows us to progress forwards and backwards through the frames. So I'm just going to give you a few minutes to run that and check that everything's working. So here we have the output for exercise 1. As always, you can see a description of what the exercise involved. This first box here is just formatting that matplotlib inline render. It gets rid of some of the extra stuff like banners at the top and bottom. I personally find it just makes everything a little bit neater. The next block here is the main one. So we've got 2 utility methods which I've included in the utility file which you'll find in the repository. The first one is just loading the images that we've downloaded from the Cell Tracking Challenge, and the second one is loading in this untracked coordinates CSV file. We then print the top 10 rows of that coordinates table just to check that it looks sensible, and then we create the spot overlay video that we just saw. And again, that's using the show overlay method from that utilities package. So just run that now. See it reading in. So we've got those top 10 rows, which of course all are for frame 0. And then we've got this render, which we can move forwards and backwards through time. We should now have a pandas data frame of coordinates that we've loaded from the repository. The focus of exercise 2 is going to be extracting out the row indices from that data frame corresponding to a particular frame or a particular time point. For example, if we wanted to pull out all the row indices corresponding to frame 0, it would look something like this. So we would be wanting a list of numbers from 0 through to 22, because those are all the rows within that data frame which correspond to that time point. At the bottom here, you'll see the aims of this exercise. This is a typical sort of format now that we'll be using going forward. So there's a description, so create a function to get a list of row indices corresponding to coordinates in a specific frame. We get arguments, so these are the inputs to the function that we're going to be writing. So for this, we want to be passing in that coordinates data frame and also the the frame number that we want to be extracting the row indices for. And then the returned value is going to be a list of row indices, so these values here, locating the relevant points in the coordinates data frame. Obviously now you can pause the video and just have a go at implementing this. Don't forget that you're welcome to look at the instructor version if you do get stuck, or you can obviously just unpause the video and see how I go about doing this. Okay, so let's have a look at one way of doing this. At this point, it's worth noting that in addition to the aims that I just listed out on the PowerPoint, if you look at the Jupyter Notebook, there is an additional section on notes which gives some examples of relevant code. So for example here, I gave an example of trying to identify all row indices with frame values greater than 7. Now, not exactly what we're trying to do here, so obviously we want to give you something to work on. It does give you an idea of the sort of format that you needed to use. So in terms of what we've actually got, we've had the definition of that function there. So input is the coordinates data frame and the frame number we want to extract for, and then we can put in our code here and return that value. The nice thing about using this structure here is that you don't necessarily have to have exactly this. As long as you're taking the same inputs and giving the correct outputs, the test space here should still run. So the way that I did this was to identify the frame, which is equal to the input frame value. So coords.frame is just pulling out that entire column from the coordinates data frame and the dot frame column. So if we just scroll back up quickly, you'll see there's a frame column. So using that dot notation to identify that column by its name. So what we get from this is a conditional check of all columns, all rows of the frame column, and check whether or not they're equal to frame. And then this coords.index function returns a list of the indices for that data frame where this was true, i.e. it's just going to give us a list of row indices where the frame was equal to frame. So if we run that, we shouldn't see anything because that's just the definition of the function. But now if we run this, what we're doing is, again, we're loading in that coordinates from file. The reason for doing this at the beginning here is just so that if we've changed anything, we're starting with a fresh copy. So loading in the coordinates, setting frame equal to 0, and then running our method here, or our function that we've just defined. So we're identifying all rows corresponding to frame 0, and then we're actually going to run it immediately again for frame 1. So if we run that now, we see that we've loaded in our coordinates and we've got the row indices for frame 0 and then the row indices for frame 1. And there's a bit of a sanity check. You can see that the first index here follows straight on from the last index there. Now on to exercise 3. So at this point we're able to extract out the rows corresponding to a particular frame. For the very first frame, we don't have any existing tracks that we can link back to, so we assume that each of the objects detected in that first frame are the first instance, or we're going to call them the first instance of each track. So what we want to do is to write a new function which allows us to identify any of those specified rows which have a track ID equal to 0, i.e. they've not yet been assigned a track ID. And we want to take those and then give them a unique number. So the aim of this is to assign a unique track ID to all the rows in the data frame matching the provided rows. And then we want to take arguments, which is again our coordinates data frame, and also that list of row indices that we got from exercise 2 corresponding to a specific frame, in this case frame 0. And then there aren't any returns from this because we're actually modifying the input data frame. So we don't take the data frame in and put it out, we're actually updating the input value. As with exercise 2, the notes for exercise 3 give a bit of a clue as to one of the functions that you might want to use. So in this particular example, we're extracting out the maximum value in the x column. So in our actual implementation, what we wanted to do was to use this same notation to get the current maximum track ID that's been previously assigned. The reason for this is that we're now assigning new track IDs, i.e. for tracks that have never been seen before, so they want to have a unique ID number. So we pass in that coordinates data frame, get the track ID column, and then extract out the max value, and that is assigned to max_ID. After this, we're now going to iterate over all of those row indices corresponding to the currently specified points, and then we're going to check if their track ID, so if coords.trackID at that particular index is equal to 0, it hasn't been assigned before, we increment that max ID by 1, so max ID is equal to the previous value plus 1, and then assign that value using the at function for pandas to that point row index. So effectively, we're saying let's increase the max ID by 1 and then assigning that value at that particular index if it was previously 0. So to test this out, we load up again the new coordinates array copy or a new data frame. For frame 0, we get the current row indices, and then we use this new function assign new IDs, passing in that data frame and the indices we've got from the previous function. And as before, we're now just printing out the top 30 rows. So you can see here all of the frames corresponding to 0 now have increasing unique track IDs, but the rows corresponding to a frame of 1 still have nothing. And that's because in the next step, we're going to be extracting these rows out and then trying to link them back to whichever is the optimal coordinate in the previous frame. Exercise 4 has been split into 2 bits. So in exercise 4a, what we're doing is identifying the row indices corresponding to the most recent instance of any track. So it doesn't matter how long ago we last saw it, it could be seen 20 frames ago, we're still going to consider it to be an active track. In part 2, or 4b, what we're going to do is just say we're only going to consider those tracks which have been seen within a certain time window. So say like the last 5 frames. Anything before that we're going to assume is a dead track and we're just going to ignore it. So the way we're going to do this is we're taking our table of semi-tracked coordinates. So this is the example table that we saw a little bit earlier on, which we're sort of skipping forward in time. So let's assume that we've tracked all the way up to frame 49 and now we're looking at frame 50. The reason for doing this for the purpose of this demonstration is that if we were to just use frame 1 tracking back to frame 0, well, all of the points in frame 0 are going to be available and it doesn't really demonstrate the concepts. So by here using track data that's already tracked halfway through the video, we're able to see the effect more of linking to different frames. So what we want to do is we're going to identify from our track ID column. So as we say, we've got unique track IDs detected all the way up to the end of frame 49, and then 50 and onwards they're all 0. So from those IDs we want to find out what the unique values are, because of course you'll get repeating values through this. You can see here track ID 5 appears in frame 46, 47, 48, but not 49. So we find that there's 2, 3, 4, 5, 6, 8 and 9 are the unique track IDs, at least in this little window we're looking at. Then we identify the most recent instance of each of those. So 3, 9, 4 and 8 were available in the previous frame, frame 49. 5 and 6 were one frame before that in 48, and number 2 was available in frame 47. And then it's a case of pulling out the relevant row indices, similar to what we were doing previously, corresponding to those most recent values. The arguments for this are simply just going to be the coordinates data frame, because we're just identifying all available tracks. We're not considering any sort of frame window. So there's just a single argument for that particular function. And then the return is going to be a list of row indices for those most recent instances. Okay, so again, we've got a few example bits of code here. This time I'm not going to go through them. I'll let you read the information about those at your own leisure. So the method definition that we had here was simply that it's called getAllTracks, and it's accepting a single argument, which is that coordinates data frame. So the first thing we want to do is to get a list of the track IDs, like all of them. So that's simply just calling coords.trackID, and then using the NumPy unique function to identify the unique values within that. So in the previous example, it was 2, 3, 4, 5, 6, 8, and 9, I believe. Next, we're going to create an empty array, which is the track rows, and then we're going to iterate over each of those unique IDs, and assuming that it's not 0, because it will still identify those 0 values corresponding to unassigned tracks as a unique ID, so we want to skip that. Assuming it's not 0, we're going to get the instance of all cases of that track ID. So 5, for example, we know will be available in a few frames. So we say what is coords.trackID equals this current unique ID. We get the index of that and we store that as the instances, and then we're just identifying the most recent case of that. So we can use this -1: notation to pull out the final instance of that index. And that just gets appended to this nascent array here, which in the end will be returned. So what we're getting there is simply a list of the most recent indices corresponding to each of the unique track IDs. Again, we're going to run this, so loading in a fresh copy of the coordinates and then just running this. So what we see here isn't simply the list of the row indices, it's actually the locations, because I'm using coords.lock, so this location and then that row that list of row indices that we've got from our function. So what that does is it prints out the relevant rows of the coordinates data frame, and we can see that indeed each of our track IDs is present, and it should be the most recent case, so it's 49s, 47s. The one interesting one to note at this point is that we've got one that hasn't been seen since frame 16, and it's in exercise 4b that we should get basically the same data frame out, or the same block here out, apart from that one there. So exercise 4b is very similar to the previous one. We're just going to introduce basically a frame filter in terms of the range of frames that we're going to accept as still active tracks. So we start off in exactly the same way, pulling out that list of track IDs, identifying the unique values, getting the most recent instance of each of those IDs. What we add in is a filter to say, in this case, we're only going to consider those track IDs which are within 2 frames of the current frame. So we're currently at 50, so we're only going to consider those that were present in frame 48 or 49. And here this means we're discarding this one which was present in 47. And then from those we extract out the relevant row indices. So this is the same as before, but we're now just missing this 4, 5, 6. Arguments wise, we've got the coordinates data frame as well as the start and end frames for which we're going to consider tracks to be active. Again, anything outside that is just going to be ignored. And then the return is the same. It's simply a list of row indices for the most recent instance of the available tracks. The method we generate for exercise 4b, very similar to the one we were doing previously in 4a. The only difference here is we've got a couple of extra arguments specifying the first frame and the final frame, which indicate the range over which we're going to consider tracks still to be active. Rather than what we did last time, which was simply to go np unique on all, like the whole contents of the track ID column, now we're going to generate a subset. So here we're just getting the row indices for frames which are greater than or equal to that start frame and frames which are less than or equal to the end frame. So this will just be all the row indices for any coordinate which is present within that time window. And then when we call this np unique, we're going to specify a subset here, so track and then square brackets, rows. And so that's only going to give us the unique track IDs which were present within that time window. Otherwise, everything else here is exactly the same. We're iterating over the unique ID numbers. We're ignoring any that have been unassigned, thus have a track ID of 0. And we're getting all the instances or all the indices corresponding to instances of that particular ID, and then we're just appending the final instance that we found onto this nascent available rows list, which gets returned. So now when we run this, we get something very similar to last time, but whereas last time we had that one 376 from frame 16, now that's gone, but otherwise everything should be exactly the same. At this point, we've managed to generate 2 sets of row indices. The first set corresponds to the most recent instance of each track. The second set corresponds to all the points which are available in the current frame. What we want to do now is take these row indices, extract out the relevant coordinates from the coordinates data frame, and calculate the cost of linking each of the points from the previous tracks to the points in the current frame. What we do is we use the Hungarian algorithm, said before, also known as the Kuhn-Munkres algorithm. We use that to calculate what the optimal assignment of all those points is, such that we're only able to assign one previous track to at most one current frame point. Right now we're not actually going to do that, but I'm just going to talk through a little bit of the logic about how it works. In this particular exercise, we're literally just going to calculate the cost between 2 specified points. So say we've got these 2 sets of points, and if we just overlay them together, so we're assuming that the ones shown in blue are from the available tracks and the ones shown in green are from the current points, we go through pair by pair calculating what that cost is for each of them, and then this goes into something called a cost matrix. So each row here corresponds to one of the track points, and each column here corresponds to one of our present points. The cost can be pretty much anything you want. Most commonly, it's just going to be this sort of the Euclidean distance, the straight line distance from the centre of one object to the centre of the other object. However, you can add in additional information if you want to weight it for things like area. Like previously, we mentioned that the coordinates data frame actually includes the area measurements for each of those detected cells. This is because you might want to weight it such that it's very unlikely that a cell would go from being really small in one frame to suddenly very large in the next frame if there was another option available that would allow it to maintain its size. Similarly, you might have, say, intensity measurements if you're looking at fluorescence microscopy data, so you might want to weight on those intensity measurements. What we're going to do in this exercise is just calculate the cost based as the straight line distance between 2 points, and for that you can see the equation here. So the distance between those 2 points is equal to the square root of the squared distance in x and y added together. The arguments for this particular function are going to be the coordinates data frame, the row index for one of the points, in this case the last instance of one of the tracks, and the row index for one of the current points, and also a distance threshold, because we know that things aren't necessarily going to jump from one side of the image to the other. They're probably only going to move 20 or 30 pixels maximum, and this allows us to prevent cases where we get erroneous links where maybe one object disappeared in one frame and another object appeared at the other side of the frame. The Moncrief algorithm by default would just try and link those, even though it's very unlikely and there's a high cost associated. So we have to introduce a distance threshold. The return value from this is going to be a single floating point value corresponding to the cost for linking these 2 points. By floating point, I just mean like a decimal as opposed to an integer, and this is going to be set to infinity if it's greater than that threshold. So for this one, it's relatively straightforward. We've got our calculate cost function here, inputting the coordinates data frame, the row index for the most recent track, and the row index for a particular current frame for a particular point, and this distance threshold that we're imposing based on what we know about this system. Like this will depend on what you're looking at. If you're looking at cells which are moving very slowly, maybe you have this set to 3 or 4 pixels. If you're looking at something actively swimming, it might be a much larger distance. So what we do here is we're going to calculate the distance in x between these two. So we extract out the x value for the point index, and we extract out the x value for the track, and that subtracting the two will give us dx, and then likewise we do the same for y, so dx dy, and then we use the equation from the previous slide, so multiplying the two together, or squaring them, and then taking the square root of that value to get this distance. And then finally, we're just going to check if that distance is greater than this specified threshold. If it is, we just set d equal to that infinity value that we initialized in exercise 0, and then return that. In our test space, we load up another copy of the coordinates, and we get the row indices for frame 0. And just for the sake of argument here, for the purpose of demonstration, I'm just going to pull out that first copy of the points in frame 0, and then we're just going to display that, and then going to do the same thing for the first point in frame 2, index 1. So now we've got our 2 points, so let's say this is from the previous frame, this is from the current frame, so that's kind of like your track, this is your current point. And then we're going to use our new function, calculate cost, passing in the coordinates data frame, the index of the previous point, the index of the current point, and our distance threshold, which here is set to 10, and it will print out our cost along with the threshold. And then what we're going to do is do the same again, but with a much smaller threshold. So first time round as a threshold allowing us to move 10 pixels, and next time round it's a very small threshold allowing us to only move half a pixel. So if we run that, we can see here that coordinate 1 was at 19.58, 50.83 in x and y, and then the second point was at 20.29 and 50.70. So two very similar points, and indeed you can see that the cost, or in this case the distance, was 0.72 so on. However, if we told it that we're only going to allow links up to 0.5 pixels, which is unrealistically small, but here just to sort of show what happens if it's a value above that threshold, you can see here it was set to that same value that right at the top we defined as being infinity. Exercise 6 effectively just takes what we did in exercise 5 and loops it over all the possible points that we had. So it's looping over all the previous track indices and all the current point indices. When we do this, what we're going to do is we're going to calculate the cost using the function from exercise 5, and then we're going to assign that value into a 2D array. So the arguments for this, again, as usual, are the coordinates data frame. Now, rather than specifying a single index for the track and a single index for the current point, we're passing in those lists for the indices of the tracks and indices for the points that we've generated in the previous exercises, and that same distance threshold. What we get out of this now is this 2D array containing all of the costs for all of those possible combinations. So effectively the same thing that we're looking at up here. So for this one, what we're going to do is we're creating this method called calculate cost matrix. As I previously said, we're taking in the coordinates data frame, the list of row indices for the most recent instance of each track, the row indices for all the current points, the points in the current frame, and this single distance threshold. So first thing we want to do is use the np numpy.empty function to create a 2D empty array. So this will have number of rows equal to the number of tracks that we've got, and it will have a number of columns equal to the number of points that we've got. Then what we do is we iterate using nested loops over all of those track indices and all of the current point indices. I'm using this enumerate function here, which additionally gives us the index, so a separate index, not to be confused with the row index. So it gives us a separate index for the current iteration count. So it will be first time round, it'll be 0, then 1, then 2, then 3. This is useful because it allows us to access the different rows and columns of that cost matrix as we go. So if we look at this, first time round, we're pulling out that first track row index from the pandas data frame. This is going to give us a 0 for the track I, and it's going to give us the relevant row index. For that one, we then are going to loop over all of the available points, again getting a different iteration index and the row location. So we're passing that track row and point row from here and here back into that function that we generated in exercise 5. So that's the one up here. So a single track row and a single point row, and that's going to give us that distance value. And that distance value that here we're calling cost is entered into that empty cost array at the relevant location. So this is why we were getting those track I and point I indices. So to start off with, we're going to be populating row 0, then row 1, then row 2, and for each of those we're iterating over all of the available points, so it would be column 0, column 1, column 2, and so on. And then we're just returning that back out as the cost matrix. In terms of running this, as usual, we're reloading in our coordinates. We're getting the row indices for frame 0 and frame 1. And then here I've just assigned a threshold of 20, and we're going to calculate that cost matrix for those row and for those track and point rows. Here we're using a slightly different data set. This has just got a lot less data in it, which allows us to visualize that matrix in a much more succinct way. So I'm going to print out that matrix, and then we're actually using the SciPy linear sum assignment solver, which we imported right in exercise 0 to calculate our assignments, and we'll be using those assignments later on. You don't need to worry about what they look like right now. So here you can see that we've loaded in our data, and these are our costs. So there were 3 tracks and 4 points, each of these relevant costs. And there should be in here yet at least one instance that was over the threshold. So that's our fake infinity value, as is this one here and this one here. So only this value, this, these, and those two are actually sort of valid targets for linking. And then, like I say, we'll look at that assignment matrix at the beginning of exercise 7. So for exercise 7, what we're trying to do here is we've now run the linear sum assignment solver, which is SciPy's implementation of the Hungarian algorithm. We're going to take the assignments from that and inherit the track IDs into the current points. So we've got our cost matrix here, and the linear sum assignment solver has decided that this is the most optimal configuration, which gives us at most one track being linked to one current point. And you could see that, yes, this makes sense. That combination there gives us a very low residual. All the costs here are no more than 3. The way this is going to be output, and what we saw just at the end in the output of exercise 6, is that we have a 2D array where the first column here corresponds to the track index. So here for the first row it's 1, then 0, then 2, then 3, and then the corresponding point. So for 0, 1, 2, and 3, because that just goes top to bottom. So each of these are a pair. So if we just look at that one again, that would be 0 and 1. So what we're going to do here is for each of the points, it's going to inherit the track ID of its assigned track. So if this had a track ID of 17, this point then would also inherit the track ID 17. The arguments for this, as always, are the coordinates data frame, the row indices for the tracks and points to be linked, and the cost matrix that we calculated from exercise 6. And again, as with, I think it was exercise 2, we're not actually going to return anything simply because we're going to be updating the track indices, or sorry, the track IDs of that input coordinate data frame. Okay, so for exercise 7, we've generated this method here, which is assign IDs. This is accepting in the coordinates data frame the list of track rows and point rows and that cost matrix, the 2D cost matrix that we generated using the function from exercise 6. You've already seen the use of this linear sum assignment function from SciPy. That was just in the test space of exercise 6, just to show you what you got. In this case, it simply linked this one, and this one has been the optimal assignment in terms of the summed cost. So you can see here that the tracks and the rows, so this has been transposed, but the tracks and rows are 0, 0, so it's linked that to that, 1 to 1, and 2 to 2. So what the function here does is it calculates that assignment, so that's 2 pairs of assigned indices, and then we're going to iterate over each of those pairs. So for this I'm using the zip function, and that just combines those two 1D arrays together. So the first one being the track indices for the assignments, and the second one being the point indices for the assignments. And then on each iteration of this loop, it gives me the corresponding pairs. So it gives me the first track assignment and the first point assignment. Then next time around, it will give me the next, like the second track assignment and point assignment, and so on. So they're coming out as pairs. I then access those relevant sections from the cost matrix, and assuming that value is less than infinity, or our fake infinity value, I pull out what is the track row and the point row for that particular assignment. So these here correspond now back to our original coordinates data frame. So these indices here correspond to the assignment matrix, to the cost matrix, whereas these ones here correspond back to our coordinates array. It's then a case of identifying what the track ID from for that particular assigned track was. So this is the track ID that we want to be inheriting and passing on to the assigned point. So here we're just going coords.trackID and then pulling out the row corresponding to this particular assignment. and then I'm putting that into the track ID value for that particular point, the current point that's been assigned. So we're just taking the track ID from the assigned track and inserting it into the current point that it was linked to. In terms of the test space, again, we're loading in a fresh copy of the coordinates. I specified a few bits here. So let's say we're working at frame 50. So again, we're working with that partially tracked coordinates data set, just as a bit more interesting. We're only allowing it to track back up to 2 frames, and we're allowing points to move up to 5 pixels between frames. I'm then specifying what the start and end points are. So these are relative to the current frame. So if the current frame is 50, the starting frame is 50 minus 2, and the end frame is 50 minus 1, because we don't want to be considering our current frame. Now we're getting the available tracks for, so we're specifying the coordinates data frame and the start and end. So this is the one from exercise 3 or 4, get available tracks, so 4B. And similarly, we're getting all the current coordinates. So this is from exercise 2. So it's just the current coordinates in frame 50. So these are our 2 sets of row indices. Then we're using the calculate cost matrix function from exercise 6 to get that 2D cost matrix. And we're now using the assign IDs that we've just generated in exercise 7 with that data frame, the lists of track and point indices and our 2D cost matrix. And then after all of that, we should get out our assignments. One final thing that we do is to assign any of the points in the present frame which has still got an ID of 0. We're going to assign to a new, we're going to assign them a unique track ID. That's because if anything here failed this less than infinity test, it just wouldn't have been linked, and so that particular point wouldn't have inherited a track ID, so it's still set to 0. So this is where we use that assign new IDs function just to give it the next available track ID. So that now becomes a new track that can be linked to in subsequent frames. So here we see the coordinates data frame for the current points. So everything in frame 50, and you can see at least one instance there where it wasn't linked, so it's 0. And so following the new track creation, that has now been assigned to value 35, which should be the next biggest one, yeah, because the previous largest value was 34. So our final exercise is a little bit different again. Whereas before we were taking a prescribed method format and then implementing that and then running it in a predefined test space, what we're going to do here is effectively create the test space ourselves. So we're just going to use all of those different functions that we've previously created, stitch them all together and just loop them over all available frames. You actually saw a large portion of that pre-prepared in the test space for exercise 7, where we're starting to incorporate a lot of the different functions that we've created. So really the key thing here is to just put that inside a loop and have it iterate over all of the available frames. So what we'll get out of that at the end is hopefully a video that looks something like this. So we saw this at the beginning of the presentation where you've got all the different tracked cells. Let's just play that again. All the different tracked cells with a unique colour being printed behind them. Now, for our final exercise, as I say, all we're doing is basically taking that test space and fleshing it out. So first couple of bits here are just a bit of housekeeping. So again, this is just formatting matplotlib to behave as we want, and also just changing how NumPy prints values. So in this case, we're telling it a precision of 3. We're again specifying some parameters. So here, things are actually allowed to link back up to 3 frames, and we're going to give it again a distance threshold of 5 pixels. We're now loading in the images and the coordinates, and for the very first frame we need to initialize the tracks. So if you remember, I said that the tracks in the first frame, obviously they've come from somewhere, but we don't know what their track IDs are, so we're just going to initialize those with the first, whatever it is, 22 values. We also need to count how many images there are, so we know how many times to run our loop. So in this case, we're just taking the shape of the images stack. And here it's just a case of running a loop where frame is our value in the range 1 to the number of frames. And what goes in there is basically just the same content that we had in exercise 7. So rather than specifying a hard frame value, this is coming from our loop and it's going to change on every cycle. We specify the start and the end frame, we get the available tracks, we get the current points, we've got this threshold value. This actually is fixed, so it could go up here as well. We calculate a 2D cost matrix and then apply our assignments, our ID assignments based on that cost matrix and assign anything that was unlinked. So if we run that, and then the final bit will just be plotting. So you can see it reading and processing. There we go, so that should be done. And now we're just going to render that, and that hopefully shows our colourful track overlay. Cool. So at this point, we've done with this particular session. I'd like to say thank you for following along and reaching the end. If you've got any questions, you can contact me at stephen.cross@bristol.ac.uk. I've also got my personal GitHub page here, and also the GitHub for the Image Analysis Focused Interest Group of the Royal Microscopical Society. This is the group who ran the Python course back in December. I've also got the facility webpage from where I work, and also the Royal Microscopical Society's page listed down there. And yeah, thanks again.